I'm standing near one of the depleted uranium hexafluoride cylinder storage lots. And these are a few of the 46,400 cylinders that have accumulated at the United States Department of Energy facilities in Oak Ridge, Tennessee, Paducah, Kentucky, and Portsmouth, Ohio. I want to take a little time and answer some of your questions about what is depleted uranium hexafluoride. Where does it come from? And what would happen if it is exposed to air or water? Let me start out by explaining what is uranium. There is a large amount of uranium on Earth. There is more of it than silver, used for coins, or mercury that is used in thermometers. By itself, uranium is a heavy silver-white metal, almost as hard as steel. Uranium is never found by itself. It is always combined with other elements. For example, here's the ore from a uranium mine, which is called yellowcake. Yellowcake is a compound of uranium and oxygen. It is treated with nitric acid and ammonium hydroxide to change it into ADU, a compound of uranium and nitrogen. The ADU is heated in a kiln, which changes it to brown oxide, another compound of uranium and oxygen. The brown oxide is fluorinated with hydrofluoric acid to form a green salt, or UF4. The green salt can be reacted with fluorine to make uranium hexafluoride, or UF6. Up until the mid-1940s, uranium compounds were used mainly for glazing pottery because of their brilliant colors. Uranium is made up primarily of two types of atoms, or isotopes, U-238 and U-235. These numbers refer to the atomic weights of the different isotopes. In the early 1940s, scientists at the University of Chicago demonstrated that the U-235 isotope could be made to break apart and release a lot of energy in the process called fission. The fission process was found to release a great deal of this energy, which can be harnessed and used either as a fuel to produce nuclear power or in weapons. As found in the mines, uranium contains only 0.7% of a fissionable U-235 isotope, which is not enough for making weapons or atomic fuel. A way of increasing the concentration of U-235 in uranium was needed. Several different methods of enriching U-235 were tested, and the gaseous diffusion process was found to be the most practical. As a result, during the late 1940s and early 1950s, large industrial facilities to perform this process were constructed at Oak Ridge, Tennessee, Paducah, Kentucky, and Portsmouth, Ohio. As the name suggests, gaseous diffusion requires that the uranium be in the form of a gas, not a solid or a liquid. UF6 is the only uranium compound that can be a solid, liquid, or gas at a reasonable temperature. When heated, solid UF6 becomes a liquid and then a gas, which can be fed into the gaseous diffusion process. During the processing, this UF6 gas is separated into two streams. The enriched stream will end up with an increased concentration of U-235, and the other, called the depleted, will have less U-235. UF6 is differentiated from other uranium compounds in that it will decompose when stored in the open air. Therefore, it is always handled in closed containers. A small sample of UF6 is shown in this glass tube. When it is heated to 147 degrees Fahrenheit, the solid crystals melt into a liquid, which boils to provide the gas for the gaseous diffusion process. Because only 0.7% of the UF6 fed into a gaseous diffusion plant is U-235, and only about half of that can be extracted, a large amount of material has to be processed to obtain a small amount of enriched product for shipment to a nuclear fuel fabrication plant. As a result, a great deal of depleted UF6 is left at the end of the process. Since the diffusion plant began operating, over 90% of the UF6 fed into the process has come out as depleted UF6, containing 2 to 0.3% of U-235. The depleted UF6 is stored in cylinders, which are stacked in large storage lots at each of the gaseous diffusion plants. Each of these cylinders contains 14 tons of depleted UF6 under a vacuum, or what is called a negative pressure. A cylinder has been specifically designed to be used to store depleted UF6. The design features for this cylinder, called 48G, are contained in an American national standard titled Packaging of Uranium Hexafluoride for Transport. Each cylinder is fabricated of 5/16 of an inch thick welded steel. Each cylinder has a nameplate, like this one, showing its identification number and a symbol to certify that it has been made and tested to conform with the standard. To date, there have been about 13,400 of these cylinders stored at Portsmouth, 28,300 at Paducah, and 4,700 in Oak Ridge. Let's look at how one of these cylinders is filled and stored. To make sure that the cylinder is filled with the proper amount of depleted UF6, it rests on a cart on a scale and is connected to the process piping. When filling starts, liquid UF6 at a temperature of 160 degrees Fahrenheit flows into the cylinder, and the pressure increases to slightly above atmospheric pressure. The flow of liquid is allowed to continue until the scale shows that the 14-ton fill limit has been reached. At this point, the cylinder will be 90% full of hot liquid UF6 and 10% full of UF6 gas. The cylinder valve is then closed and the pipe connected to the process cleared of any UF6 residue before it is disconnected from the filling position. Here at the Portsmouth plant, it is moved to a railroad car for a 5-day cooling period. During this time, the hot liquid cools to 147 degrees Fahrenheit and gives off enough heat to boil about 70 gallons of water and shrinks to a solid, creating a vacuum in the cylinder. Where the liquid UF6 had filled the cylinder 90% full, now the solid only fills it to 62% full. Now that the UF6 is solid, this machine can straddle the cylinder, pick it up, and transport it to the cylinder storage lot. This is a cylinder stacker that is used in the storage lot to stack the cylinders too high and arrange them in rows. Now let's look inside one of these depleted UF6 cylinders. These pictures were taken with a video camera inside a full cylinder. We see the crystals of UF6 on the bottom of the cylinder and the colorless UF6 gas above them. Notice the solids go up the sides of the cylinder and stop in a straight line. This marks the level of the liquid UF6 when the cylinder is filled. As the liquid cooled and turned to a solid, it shrank to the level we see here. Looking at the inside surface of the cylinder, you will notice that there are no pits or evidence of corrosion of the metal. This is because the hot 160 degree Fahrenheit liquid UF6 that was first admitted to the cylinder wet the entire inner surface and reacted with the iron in the steel to form a very thin surface layer of the chemical iron fluoride. This reaction forms a protective coating on the steel that prevents any internal surface corrosion by the UF6. What would happen in the unlikely event that an opening should develop in the gas region, as opposed to the solid region, of one of these cylinders? These pictures were made to simulate this condition. The workers are following the normal procedure to replace a valve on a cylinder containing 14 tons of UF6. One person loosens the valve and removes it, while the other man is ready to screw in the replacement valve. Because of the vacuum in the cylinder, none of the UF6 is released. Why?
because air moves from areas of higher pressure to areas of lower pressure. Therefore, the outside air at atmospheric pressure will flow into the cylinder. For this demonstration, to illustrate the confining aspects of the vacuum in the cylinder, the worker removes the new valve to allow additional humid air from the room to be drawn into the space above the solid inside the cylinder. While the air is entering the cylinder, we will attempt to show what is happening as moisture in the air reacts with the gaseous and solid UF6 inside the cylinder. This is a demonstration in a laboratory hood. A plastic tube containing a small amount of solid UF6 is cut and the material poured into a glass dish. The white fumes that you see are composed primarily of hydrofluoric acid, or HF. It has been formed by the reaction of the UF6 with moisture in the air. The fumes also contain some microscopic particles of uranyl fluoride, UO2F2, which is another compound of uranium, oxygen, and fluorine. As time passes, you see some of this yellowish solid material depositing on the dish. As it absorbs additional water from the air, it swells and flakes. But that is all that happens to uranium. The gray coloration on the upper part of the dish is caused by the glass being etched by the HF. What we are seeing is the slow reaction of solid UF6 with water vapor in the air. What would happen to this experiment if the water were a liquid instead of a vapor? After pouring a few ounces of water into the dish, the fuming stops, and most of the solids rapidly dissolve into the water, creating an orange-colored solution. Now, back to the cylinder with no valve. It is still drawing in air through the 1 3/8 inch diameter opening. The flow slows down as the pressure inside the cylinder approaches the pressure of the air outside the cylinder. You can begin to see the white fumes of HF inside the cylinder at the bottom of the valve opening. Occasionally, some of the HF cloud will puff out of the cylinder. The reason for this is that a small amount of heat is created by the UF6 water vapor reaction, and this can increase the gas pressure in the cylinder to slightly above atmospheric pressure. Continuous samples of the air above and below the valve opening and 10 feet from the cylinder were taken during this demonstration. The analysis of the samples indicated that the respirators are required for the workers doing the valve change. However, no protection would be necessary for anyone 10 feet or more away from the cylinder. To demonstrate that the pressure increase is very small, we see that a piece of duct tape placed over the opening is able to stop the release. No more pressure builds up inside the cylinder because no more water enters, and all the water that had entered has reacted. What would happen if a cylinder of UF6 being moved across a bridge were to fall off the truck and into the river, breaking off its valve? This type of accident has never happened. A cylinder is 63% full of solid, and the solid is in the bottom of the cylinder, causing the center of gravity to be such that the cylinder will come to rest on its side on the bottom of the river with the valve uppermost. A laboratory experiment was conducted in Oak Ridge to simulate the situation and get an idea of what might happen. This is a glass bottle containing about 2 pounds of solid and gaseous UF6 under vacuum that has been submerged in water and the tip of the glass neck broken. The vacuum drew water into the bottle. The water reacted rapidly with both solid and gaseous UF6 to form a yellow-colored solution of UO2F2 and an orange band of an insoluble uranium compound. No more water could flow into the bottle, so this is all that happened. What would have happened if something would have punctured the bottom of the cylinder that had been accidentally submerged in water? Here we see a small UF6 cylinder that has been filled with about 4 pounds of liquid UF6 and allowed to solidify with the cylinder valve downward, causing solid UF6 to cover the valve port. For this demonstration, it was submerged in a glass vessel full of water, and the valve removed. After about 2 hours, during which time the water was agitated with the motor-driven agitator, little or no reaction was evident. As we see here, what had happened was that a flood of uranium compound had formed beneath the valve. This compound would not dissolve in water, and thus was able to effectively seal the opening. This was a small-scale laboratory experiment. Would this same kind of reaction happen if a full-size cylinder were damaged? At the 3 diffusion plants, there are about 46,400 depleted UF6 storage cylinders. There is an aggressive cylinder inspection program aimed at assuring the integrity of them.
At the 3 sites during the past 40 years, only 7 cylinders have been found that required repair. Each of these cylinders had the same plugging material that was shown in the laboratory experiment.
With these words and pictures, we have followed uranium from the mine to the storage lot at the gaseous diffusion plants. Along the way, we have looked at some unique characteristics of uranium to help you have a better understanding of what depleted uranium hexafluoride is, where it comes from, and what happens if it is exposed to air or water. Careful management of these characteristics allows uranium to be safely processed, used, and stored.